For this first day's lecture, I'm recording from my office. I did do it in class, and I think given the audience in the summer, I want to be able to say a few things that are a little different in introduction. So our first topic is time value of money, and it's actually chapter 6 way back in your textbook, which you should have. And tomorrow's lecture is also on this same format in the office, and most of the lectures are in class where I feel it's fine for those lectures to stand as they are in the recording. So I hope you've all gotten the HP 10B2 calculator. It's a Hewlett-Packard calculator that is inexpensive and very robust, very sophisticated in terms of our needs. And the other thing I point out here in the beginning of our notes is that we certainly will not be using tables. I understand that many instructors prefer to use tables when talking about time value of money. My idea is that they are not at all used in practice, and really we're shortchanging students who already have a firm foundation in mathematics and exponential algebra. And I presume you all do, because we require calculus. We require certainly our students to have a high school knowledge of exponential algebra. So I use a mathematical approach, and the reason I do that is because over years I've learned that students learn time value of money concepts far better if they use a mathematical approach. The problem with tables is they obfuscate really student understanding. Often you get questions like, well, which table do I use? Do I use a present value table, future value table, and so on and so forth? The other thing is that tables are unduly restricting in terms of their reality, because the table factors are based on n's that are integers when they can be fractional. Interest rates don't have to be whole numbers. They can certainly be fractional, and so on and so forth. It's just far more realistic. So I trust you'll understand my reasons for using a mathematical approach. And we're going to be using this throughout the course. There are many concepts, I should say many topics, that use time value of money concepts. And so having a firm foundation in those concepts is going to be crucial to your understanding of later material. So I start out here with some variable notation. I don't want you to get intimidated by all these little symbols and abbreviations, and just flow with me as we work through problems, and you'll see what we're up to, I think. So one of the first things we're going to talk about then is the future value formula. So the future value of $1 is given here as 1 plus the interest rate to the positive n power. The interest rate I is going to be the annual interest rate usually, but in general it's going to be the interest rate per interest period. So if the annual rate is R, where I give you an annual percentage rate, R, and you divide it by C, and C is the number of interest periods per year, we're going to deal with I in a general form that takes into consideration certainly cash flows that occur and compounding that occurs more often than 1 year. Okay, future value will denote future value PV will, FE will denote future value, PV will denote present value, CF will be cash flow, and I'll have some other notation as we go through this. So our first question is, how much will $1,000 accumulate to after 1 year at 10%? If you had $1,000 and the interest rate is 10%, you're going to have $1,000 times 1 plus the interest rate, or you would have $1,100. So that's after 1 year. And the $100, of course, is 10% of 1,000, so that's $100 of interest. And I ask her, after 2 years, what you'd have is 1,000 times 1.1. That's what you have after 1 year. But then whatever that is grows for another year at 10%. So really you're multiplying it by 1.1 again. And that equals 1,000. Since the 1.1 is multiplied by itself, it's 1,000 times 1.1 squared. And you get $1,210. So it's not just $1,200, it's because you have not just $100 of interest like you had in the first year, you have $110 since the amount you started with was $1,100, and so you get 10% of that. And $1,000 after 3 years is multiplied by 1.1 after 1 year. After 2 years you have that. After 3 years you have that, which of course equals $1,000 times 1.1 cubed, which you get 1,331. Now, aside from a financial calculator, if you just have a regular calculator that has exponential functions on it, you would just say, type in 1.1, hit the X to the Y button, maybe it's a Y to the X button, but hit that button, enter 3, and then equals, and then that's multiplied by 1,000. So just to review your memory, you review the concepts you've already had, you should be able to get that just with exponential functions on a calculator. And so I asked, well, what's it going to amount to after 35 years? So now that we know that 1,000 is multiplied by 1 plus the interest rate raised to the number of years or periods for which compounding is taking place, this would be 1.1 to the 35th power. And if you take the time to do that on your regular calculator with the exponential function, you would solve it to be 28,102. Okay? Now, one of the things about a table is you would have to have a factor for 35 as n. Of course, 10% as an interest rate is not unusual, but the mathematical approach which specifies an equation is general, and it doesn't have to limit you to what's used in tables. Tables are not used in practice in the financial services industry, and I feel very strongly that our students who graduate, they're not going to be using tables at all, ever. And even though we use it as a teaching device, it's not really all that helpful to learning, but it's also not that helpful. It's not helpful at all when you're trying to extend it to what you're going to be dealing with in real life. The next question I asked for is, what about 40 years, but interest is compounded semi-annually? Well, what that means is that 1,000 after 6 months will grow to 1,000 times, you would take the interest rate in half because it's semi-annual. So half a year's interest is 5% since the annual rate is 10%. And so that's what you'd have after half a year. But in a 40-year time frame, how many 6-month periods are there? There's actually 80. So you would have to raise this to the 80th power. And so if interest is compounded semi-annually for 40 years, your $1,000 amount would accumulate to $49,561. Okay? So let's just show how that could alternatively be done using what's called an effective interest rate for the semi-annual compounding. The effective annual rate, what we could have done is said, well, The annual rate, if you have semi-annual compounding, can be figured out by taking $1. If you had $1 invested in an account that earns 10% per year, what would you have in 6 months? You'd have $1 plus 10% divided by 2, or 5%. So $1 invested at 10% after 6 months would amount to that amount, which is 1.05. But in a year, this 1.05, which is what this is, 1.05, would be multiplied by 1.05 again, just like we did this for years. In 6 months, you would have 1.05, but multiplied by 1.05 after another 6 months, or this squared. But you have to subtract the 1 to get the interest rate. We don't want the $1, we just want the interest rate. And you have to understand that the interest rate is greater than 10%. It's actually 10.25%. So the effective interest rate given semi-annual interest compounding at with an annual rate of 10% is 10.25. And so you could have solved this problem by saying 1,000 times 1 plus 10.25% is 0.1025. And that's the annual effective rate raised to the 40th power, since that's 40 years we're talking about. And that'll also give you the 49,561. All right, well, let's use your financial calculator. So you'll hear my chair squeak since I'm in my office, and I'm going to kind of relax while I talk. So anyway, what you have here is a calculator that has these functions built in it. In the top row, you'll see buttons for N. The next one is I per year. Then you have present value, or PV. Then payment, PMT. You have future value. And those are the essential buttons you'll find on any financial calculator. But I want to set you up right to start the course and keep it in this mode that I'm going to discuss, and make sure everybody's on the same setting. So the first thing I want you to do with your financial calculator, of course after turning it on, is to clear all. And the clear all is a secondary function. If you look on the left side of your calculator towards the bottom, you'll see a see all or clear all. See all differs on calculators, but we want to hit the orange key and hit that button. So when you clear all, by toggling the clear all with the orange key, you will see in your screen, probably if you just bought it, you will see 12 payments per year. And let's do that again. Just clear all and you'll see where it shows 12p per year. Now we've got to change that. And I want you to change it for the rest of the course. It'll make our lives a lot easier. So instead of 12 payments per year, what I want you to have is 1 payment per year, or 1 payment per period. And we're going to do that by hitting the 1. And you will see, again, a secondary button up on the upper right-hand corner of your calculator buttons, a C, or a clear all. I'm sorry, a payment per year, PMT per year. And so just hit the orange button and that payment per year toggling function. And then now, after doing that, if you hit clear all, that is the orange with the clear all, you should see 1 payment per year showing in your screen. It'll just blip. It'll just blink, shortly. And so I'm going to take a moment here, since I can't deal with you in person like I could a class, to make sure you get that right. So let's go over it again for redundancy, but it's safe to do. First, clear all. That is, hit the orange key and the clear all button. And if you see 12 payments per year instead of 1 payment per year, then I want you to hit the orange key. I'm sorry, hit 1, hit the orange key, and then the payment per year button towards the top right of your calculator. And now you should see 1 payment per year in the screen. And that will stay like that for the rest of the course, which is what I want. All right, so let me do our first illustration using your financial calculator. Suppose I wanted to do this problem right here, where I have $1,000 that's invested at 10% per year after 35 years is 28,102. In any order, you can enter these parameter values. So I'm going to do the order in which the buttons appear at the top of your calculator, and as the first one on the left and the top. So we're going to put in 35 for N. So just hit 35, hit N. 10% is the interest rate. Now what you do in a financial calculator is you do not put in 0.1 for the interest rate. The calculator assumes that what you're entering is a percentage. So we put in 10 for the I button. Actually, your I button says I per year, but just ignore that. I'm going to refer to it simply as the I button. So you put in 10 for I. Again, these could be in any order, doesn't matter. I'm just illustrating the order in which they're appearing on your calculator. And then the other parameter I know is I have $1,000 now that is growing at 10%. So present value is 1,000. I'll put in 1,000 for the present value. And then I'm ready to solve the problem. So I'll hit the future value button. And what you should get actually is a negative number. And I'll explain why it's negative in a minute. 28,102. Whoops, 102. Which corresponds to the answer we got. All right, so why is that negative? Financial calculators are built to or programmed to correspond to the sign convention of cash flows. So for example, $1,000 here is received by the bank, so that's a positive cash flow for them. But then after 35 years, that $1,000 that's a positive cash flow to the bank when they receive it is paid out at the end of 35 years. So it's an outflow for the bank of 28,102. And that's why that's negative. If, instead, I had put 1,000 in from the other side of the transaction, that is, say it's you that's depositing 1,000, that's a negative cash flow to you, and then you're going to pull out a positive 28,102. So had you put in 1,000 negative in for PV, and you could try this, if you put in 1,000 that's negative, and to do that you just hit the change sign key, it's a CHS key, to change the sign of a number. So if I put in 1,000 that's negative, I'm going to get a positive number back because I'm withdrawing, I'm pulling out 28,102. Okay? All right, so what I want you to think about is time runs along a line. And if I have cash flows that I'm trying to push forward on this timeline, I'm finding their future value. If I'm bringing cash flows that are out here backward on the timeline to find their present value, that's what it's called, is present value. So our exponent that you'll notice for a future value is positive because I'm pushing it forward on the timeline. It's positive number n on the timeline. So let's talk about another problem that gives you a better understanding of the power of time value of money. And that's the next one. So you've discovered that an ancestor of yours deposited $25 in an account 300 years ago. Wouldn't you wish that? And you're the sole survivor. And I do comment to the class that, look, this is actually information that is kept public by, or kept by the state governments. Each state has lost funds that they keep record of. Say somebody that you're related to moved from one state to another and forgot about a small amount in a savings account, or didn't pick up a check somewhere or something. It's left with the state, and you can go on internet sites and actually claim amounts. In fact, I have done this we had one of our relatives die, and I just happened to check some states that they happened to live in that I knew, and found quite a substantial amount of money. It was totally a surprise, but it was well worth looking into. So anyway, I'm digressing from the problem. I just thought that was a very interesting tidbit. But this ancestor of yours deposited $25 in an account 300 years ago, and the account has been bearing an average interest rate of 5%. What is the value of your find? Now, first off, I like to write this problem like it is because it looks like this is in the past, and therefore we're trying to find a present value. But what we're really after here is to know how in 300 years, $25 has accumulated forward on the timeline. So it's really a future value problem. And so if you had $25 that was invested at 5%, and 5% is not all that unrealistic given historical returns. So the marginal productivity of capital in economics is, somewhere 3 to 5%, whether you're dealing with corn or manufacturing, whatever. So you have a 5% interest rate, and it is compounded 300 years. So you couldn't do that with a table. And if you just solve for that using the exponential function on your calculator, you would find that is equal to a surprising $56,849,903. Pretty incredible with $25. And you wish somebody had just been pretty altruistic and just kind of forgot about $25 a long time ago for you. And to show the exponential power of compounding, it says, what is the value of your find? How sensitive is this to the interest rate? So let's try 7%. Now clearly the answer is not just going to be 2 percentage points different from what we got at 5%, because it's exponential in terms of what's happening. So if you had $25 invested at 7%, after 300 years of compounding, that is 1.07 multiplied by itself 300 times, what you actually get there is $16,333,270,000. And that's just with $25. Probably the greatest mind that we know of, certainly in recorded history, is Albert Einstein. And even though he was the so-called father of atomic power, which is the greatest power we're aware of in terms of our world, he called compound interest the greatest power in the world. And why is that? It's because if you look at time and money, I'll just say this, time and on the x-axis and dollars on the y-axis. If I start with, say, $25 down here, that 25 grows and the function increases at what we say an increasing rate. So what you have is a curvilinear relationship. The rate at which it increases is determined by the interest rate. So if we have higher interest rate, of course, higher interest rates, we're going to increase it faster. The point being that as you get out here on the timeline, if I'm here, just a little bit more time will cause this amount to grow to a much higher amount. And of course, as you start getting out here, it's incredibly important that the money is growing at that rate. And I take the opportunity here at this point to really point out that, you, for the most part, most of my students are young, and while they're young, they should start saving and not just be kind of foolish with how they spend money. So save some money every week and invest it while you're young. When you get a job, have the amounts of your paycheck, say, withdrawn automatically and put into savings, and hopefully after you work for a while, you're going to be vested in some sort of plan for retirement. And those amounts will grow, and you don't even know about it because it's been withheld from your paycheck. Be honest, when you look at your paycheck, and you've all earned paychecks, when you look at it, what are you looking at? The gross amount or the net amount? Everybody looks at the net amount, which is after all the withholding. So a very clever thing for the government to withhold taxes, for example, because you don't really miss them if you don't have to write a check for them as an employee. They're just withheld by the employer and they're remitted to the government. You don't really miss them. You live on the net amount. And the same thing with savings. So the other thing that's very nice about this is if you are in a qualified retirement plan, the amounts that are withheld from your paycheck are not even taxed. So they're at the full amount. You'll get taxed later when you retire and you pull the amounts out, but that's a very nice feature, and it's something that I really try to encourage my students to get in the habit of. Save often, save frequently, save regularly, but save while you're young. I've heard it said, and I could work this out, I just haven't taken the time, but if somebody starts saving regularly out of their paychecks, and let's just take a normal interest rate, maybe 7% per year, and that's quite feasible in the stock market. One who starts depositing money from 20 years old and then stops at 35, compare that person who starts depositing at 35 and then stops at 65. The person who starts at 20 and stops at 35 will actually have accumulated more money, and it's like a lot more money, 1.5 times more money, by the age of 65 than the person who starts at 35 and continues to deposit money until they're 65. So a real lesson here is just, as far as practicality, start saving while you're young, put it away, have it automatically withdrawn from your savings account or from your checking account or your paychecks, better yet, and you'll be very happy you did. So by the time you get out here on the timeline, your retirement accounts are going to be growing quite a bit. And I've, even though I lost half my money with about most people in the United States in 2008 when the market crashed, we've well recovered, and just it's the constancy and regularity of your contributions that's going to be important. So try to be disciplined about that. All right. Let's go on and talk about present value. The present value of $1, you'll notice, is the same as the future value, except that the exponent here is now negative. Now that's the same thing as writing 1 over 1 plus I to the positive n. But I like writing it with a negative exponent instead, because it conveys to the student we're bringing something backward on the timeline instead of what we were doing up here where we were pushing numbers forward on the timeline. So a positive n is going forward on the timeline. A negative n, which is the reciprocal of the present value, is going backwards on the timeline. Okay? So let's look at some examples here. You just learned you are inheriting $500,000 from your dearly departed Uncle Slewbags. It was well stated, however, that he was concerned about the, quote, stability of the youngster, and he directed $500,000 not be paid out from the estate fund for another 20 years. So you're going to get $500,000, it's just that you have to wait 20 years. If, yet not knowing what else to do, you decide to determine if the cash equivalent value of the inheritance today, and you believe that you can invest your money safely at 6%. The question is there any way to pull that amount out now? So we're dealing with a present value situation. $500,000 is in the future. It's not going to be paid out for 20 years. What is the value today? So it's bringing it backward on the timeline. In other words, some present value today, if we were to solve this algebraically, times 1 plus the interest rate of 6% after 20 years equals 500,000. And the question is, well, what is that present value? Some amount invested at 6% for 20 years would equal 500,000. And that's called the cash equivalent value today. And the way you would solve this algebraically is first solve for this piece, 1.06 to the positive 20, and divide it into this piece, 500,000. Or, notice this, that the way to write that then is that present value is equal to 500,000 divided by 1.06 to the 20th power. And another way of writing that, which I prefer, is 500,000 times 1.06 to the negative 20. Now you can use negative exponents in your calculator just like you use positive ones. If I were solving for this number, which is my present value, that's equal to the PV, I would take 1.06, hit the x to the y button, your exponential button, could be y to the x, some calculators are y to the x. Then type in 20, but you have to change the sign of the 20, and then hit equals. And you would multiply that then by 500,000 to get the answer. And so present value, if you solve for it correctly, is 155,902. So the cash equivalent price today, if the interest rate is 6%, of $500,000 received in 20 years is 155,902. Okay, so we're bringing 500,000 backwards on the timeline, 20 periods at 6%, and that's what you get. So on your financial calculators, let's go ahead and illustrate that again. So the first thing I always want you to do is to clear your registers. And again, that's the orange key. And on the left-hand side, down towards the bottom, is a clear all. So you just hit the orange and clear all. And you should now see on the screen, just briefly, one payment per year. All right, so the parameters that we're going to enter, again, these can be in any order. You can enter them in the order you like. I'm just choosing for lecture purposes to enter them in the order that they appear on the front row or the top row. 20 will go in for the N button. %6 is the I. Again, it's not 0.06, but 6 in for the I. On your calculators, it shows as I per year, but ignore that. I'll just call it the I button. And now we know the future value is 500,000. So key in 500,000 in for future value. And we're ready to sell for present value. And you hit PV. Now again, you're going to get a negative number. Since we entered 500,000 as positive, you're going to get a present value that shows up as negative 155,902. So the interpretation is, if you put into an account that is a negative cash flow, you deposit it, so it's an outflow, negative 155,902. In 20 years, you'd get a positive 500,000. And as I said before, if we had put this in as negative, you would get a positive 155,902 is the answer. So that's the sign convention of the cash flows associated with financial calculators. Okay, I hope that's clear. Now, there is the question, is there any way to pull that amount out now? One way you could get 155,902 now is to borrow it. And if you could borrow it at 6% per year, then in 20 years, you would have to pay back $500,000, which you're getting from the will or the estate. So it would only be if you could borrow at 6%. And I'll write that down for you in your notes. If you could borrow I'm saying also because the investment rate is also 6%. And to borrow money at the same rate suggests that the institutions aren't making any money. So the intermediaries certainly will charge you a higher interest rate in reality than what you could safely invest at. But I'm just saying, if you could also borrow at 6%, then borrow 155,902 today and pay back the $500,000 that you get from your estate in 20 years. Okay? So let's look at another one. And it's kind of nice in this office. I don't have any students asking any questions or anything. I'm just trying to anticipate where the questions are and trying to explain what I can based on experience. So, as I say, I mean, the lectures, for the most part, that are recorded are going to be live in the classroom. We do have a lot of give and take in the class. I like that. I really enjoy it, and it's a little different having summer school where we're recording these lectures. But hopefully you're able to comprehend what I'm talking about here in these notes. So our question next is, you wish to have $1 million when you retire in 45 years. I think you'd all like to be a millionaire when you retire. And you're probably, say, 20 years old, most of you. So 65 is typically the retirement year. And you're asked, how much must you invest today if you can earn 9.72 annually as a compounded return? And then I'll ask the question, well, what if interest is compounded monthly or daily? Okay, so the mathematical approach always requires an equation. And we want to have something to equal $1 million in 45 years. Can you see that in that question? You want to have, that means something equal 1 million in 45 years. So something invested at 9.72% will account for that $1 million or amount to it. So some present value, we don't know what it is, multiplied by 1.0972, compounded 45 times, so we're raising it to the 45th power, is equal to $1 million. Look at that equation. Some present value grows at 9.72% for 45 years to equal $1 million. As we did in the last problem, another way of writing that is just to say the present value equals 1 million times the reciprocal of 1.0972 to the positive 45th. The reciprocal would be 1.0972 to the negative 45th. So that's an equation, and it's always an equation with time value of money. So if I solve for 1.0972 raised to the negative 45 power and multiplied it by $1,000, I would get a present value that's the solution of the problem. And you get 15,387. Now you should be able to get that just with a regular calculator that has an exponential function. And that means that if I simply deposit right now 15,387 in an account, I'll be a millionaire in 45 years if the interest rate is 9.72% annually. Now, a couple things I wanted to do with this problem is, one, to demonstrate interest rates can be very, very fractional. So here we have a very unusual interest rate of 9.72%. Again, you're not going to see that in a table. And usually textbooks, when they try to deal with a situation, since they're teaching tables like this, they're going to do something called interpolation, where they take the number between 9% and 10% and try to, linearly interpolate it. Well, that's totally inappropriate. You guys all know exponential algebra, and you can do this mathematically. And why should we shy away from what you've already learned? You should have learned this, say, in 8th grade or 9th grade with exponential algebra. And here is the great application for it. So here's the bottom line of this question. Why don't you, since you're 20 years old, your parents or somebody's paying for your education, just take $15,000 or $15,387 out. You take the semester off, just say, look, I want you to invest it at 9.72% so that in 45 years I'll be able to retire a millionaire. Now I'm tongue-in-cheek on that one. Of course, if you take off a semester, you're giving up some opportunity costs in your education and all of that. But it just shows you the power of investing in the long term. The other thing I wanted to point out about this problem is that 9.72% is really pretty realistic in the long run for stock market returns. Just to prove my point, if you go before the Great Depression, which occurred in 1929, and if you go before that, 1926, and measure the average stock market return from 1926 till, I think the study I read was 2010. So it was after the 2008 problem that we had in the markets and all that. So you're covering depressions, mini recessions, and so on and so forth. The average rate of return for stocks in general is about 10%. Now, small companies, if you invest in smaller companies, they do have a higher expected rate of return, and also they have a higher average return over that same time period. And the reason smaller companies earn a higher rate of return in the stock market is because they're riskier companies. You'll learn about this if you haven't already in your finance class. But when you have more risk, you also have the expectation of a higher rate of return. Otherwise, you wouldn't take the greater risk. So there are a couple things I wanted to bring out in this problem. If we had monthly compounding, as it's asking here, then I have to think about how I'd set this up. So my general setup was like this: $1 million times 1.0972 to the negative 45th. What would I do if I had monthly compounding? Now my $1 million is the same. But now I would multiply it by 1 plus the monthly rate. So I have to figure out what a monthly rate of return is. And that's taking the annual rate and dividing it by 12. So I think you'd agree if I had $1 million invested for 1 month, that's what I would have if the interest rate is 9.72% per year. But just like I had up here 45 years when I had an annual rate, by the way, this is 0.0972. Now I have to talk about how many months are in 45 years. That's my exponent. So the number of months in 45 years would be 45 times 12, which would be the exponent I would use. And you could solve that. And if you solve it correctly, you get 12,825. Obviously, less than 15,387, since your effective annual rate is higher if you have monthly compounding. It's even more of a difference if you had daily compounding. If I had daily compounding, think about it. If I had $1 million invested after just 1 day, I take the 0.0972 divided by, we could say 365. And as I also point out in my next lecture, banks use 360 days in a year instead of 365. They use 30 days in each month. 30 days times 12 is 360. So to be realistic here, I would divide that by 360 rather than 365. Okay, but that's what you'd have to after just 1 day. But we're investing it for how many days in 45 years? Well, that would be 45 times 360. So your negative exponent would be that product. And you get 12,608. Not a huge difference from the 12,825, but still a difference. And so more frequent compounding results in higher effective interest rates. Now, another way we could have solved the last problem is I could have computed an effective annual rate, and I'll talk more about this in my next lecture. The effective annual rate is equal to if I had $1 invested in an account that earns 9.72% per year, then what would you have on that dollar after just one day? I hope you agree that you'd have that. If I invest $1 after just one day at 9.72%, that's what I'd have. But then that multiplies by itself after 2 days, multiplies by itself after 3 days, multiplies by itself 360 times in a year. And that's what I'd have if I invested $1 at 9.72% after a year if compounding is daily. But I want the interest rate. I don't want the dollar there. The dollar is what I invest, but the interest rate is obtained by subtracting out the dollar now. And the effective annual rate then is not 9.72%, it is 10.207%, or 0.102207. So we could have gotten the answer to the last problem by using an effective annual rate on the 1 million, 1.1027, 10207. But now, since it's an annual rate, I would bring it back 45 years. And mathematically, that has to give you the same answer, 12,608. Okay? So, that brings us to the concept of annuities. Now, we'll spend a lot of time on this next lecture. These were single amounts. So I've just illustrated there are two formulas for single amounts. You have a present value of $1, which you can apply to any number of dollars, a future value factor for $1, and also present value factor. Present value is always involving a negative exponent. You're bringing backward on the timeline, whereas future value, you're pushing forward on the timeline, so it's positive. Now, the other very common cash flow situation is when you have something called an annuity. Now, an annuity is defined as a cash flow that repeats. The same amount repeats. So, for example, if you buy a house, you're going to make a payment per month, and it stays the same as long as you don't have an adjustable rate mortgage. It'll stay the same for, say, a 15-year mortgage, 20-year mortgage, 30-year mortgage, what have you. Buy a car, over 5 years, you're going to make the same payments per month. So there's lots of applications in accounting and finance where we have cash flows that repeat that are the same amount. That's called an annuity. And there are two types of annuities. I'm going to discuss this at length in the next video, but I just wanted to point out here the difference between what we call an ordinary annuity, and I'm putting asterisks here because I want you to memorize the way these look, and an annuity do. Okay, so you're given two cash flow profiles. See, these are cash flows, and they're the same amount. An end period annuity looks like this if it's ordinary. Typically, when you buy a house, you don't make a payment at the time you buy it. It's 1 month later. And then every month, you're going to make a payment. Or if you buy a car, you don't pay the first payment right now. You might put money down, but that's not your first payment. Your first payment is going to be a month later. So those are typically what we call an ordinary annuity. And the way the book, and all books do this, they define an ordinary annuity as a series of equal cash flows that occur at the end of each period. It has another name. It's called annuity in arrears. And it gets its name because the cash flows occur, if you just visualize this, it looks like this one occurs at the end of period 1, this one occurs at the end of period 2, and so forth. Whereas an annuity due is defined as a series of equal cash flows that occur at the beginning of each period. So this cash flow occurs at the beginning of period 1, this at the beginning of period 2, and so forth. And if you notice, this cash flow profile is the same one as this up here, except it's shifted backwards one period. So if we just pulled it back, it would look like this. And I give you some formulas. We'll talk about these in our second lecture. For a present value of an ordinary annuity and a future value of an ordinary annuity. You're going to have to know these formulas. They're not hard, because the present value of an $1 ordinary annuity is simply $1 minus the present value factor. That's what we were just dealing with for our present value factor. But it's all divided by I. The future value of a $1 ordinary annuity, $1, is the future value factor but minus 1. So it's flipped. Here's 1 minus, here it's minus 1. But always, again, always divided by I. The only adjustment we're going to be making for an annuity due is you just take the ordinary annuity formula but multiply it by 1 plus I. And that's the case both for the present value formula as well as the future value formula. All right, I am going to stress in our next lecture that this is really a bad definition. These definitions occurring at the end or the beginning are not really descriptive, because the end of one period is the beginning of another period, and students will often get confused. What am I dealing with, an ordinary annuity or an annuity due? And so I'm going to have you spend some time committing this diagram to memory for an ordinary annuity, and then this diagram for an annuity due. And so before our next lecture, I want you just to try to do that, and then I'll bring those differences into focus as we work some problems. So that's our first lecture. I see it's only 57 minutes. It does take about an hour 15 minutes typically for my lectures. And that's because we have a lot of other things to discuss in class. So when I do have the opportunity to do it in the office, you probably have some questions. You'll be working through your homework, and it's going to be important for you to really watch these lectures carefully. To do the work with me while I'm writing it down in your class notes is going to be imperative. I'll tell you this. I'm just going to be honest. Intermediate accounting, specifically the second half, was the most difficult course I ever took. And I say that in the context of having a master's degree, a PhD, doing all of my postdoctorate study and so forth, consult everything that I can think about. I think back to the days when I took intermediate accounting too. It's not to scare you, it's just to give you a healthy reverence for what we're about to go through. In the summer, you should have nothing else you're doing, as I will say have said in my introductory comments about the syllabus. You're going to be immersed in this stuff. You're going to be doing problem after problem, thinking about it, and living and breathing it in the summer. We have 4 weeks to cover very difficult territory. Now, getting back to what I said about this being the most difficult course, it was also the best course I ever took, because it really dealt with real life situations that I've employed throughout my life. When I talk to students that come back after graduating, they talk about how they use this all the time, particularly this subject here, time value of money, and the mathematical approach. I'll share with you about a student that recently I got together with that mentioned how important this was to him, and he's a very successful person, professional now. So don't get scared. Just have a reverence for it, and make sure you understand the importance of just immersing yourself in doing it. There's no alternative but practice. I'll talk more about this in my next lecture. And I have to say it over and over again because I hate to see students tackle on or take on an assignment such as this, but not really have the time or the wherewithal to really give it what it takes to succeed. And I really want you all to succeed. All right, so I'll finish this lecture here and we'll pick it up next time.